Welcome back. So, Weismann's evolutionary theories left coral in a pretty tight spot. It was beginning to look like they couldn't adapt fast enough to survive climate change. Sure, they could inherit germline mutations, but these were rare and only took hold over long timelines. What coral really needed to adapt fast was the ability to inherit mutations quickly, and Weismann insisted that that was impossible. But luckily for coral, a lot has come to light since Weismann's time, and consequently, there's more data than ever to help researchers solve this problem. In fact, many are looking at the very thing Weismann imagined in his germplasm, the material blueprint, now known as the genome. And by looking at these collections of genes across organisms, they're able to see how coral change or adapt over time. But will this reveal a solution to the evolutionary hang-ups we talked about in parts 1 and 2? Is there a turn in our story of evolutionary theory, one that offers coral a roadmap to survival? To answer those questions, we need to go back to the year 2020. And while I know that might sound emotionally scarring, I promise you it's worth it. Because that was the year that genomics flipped the script on evolutionary theory. You see, while COVID had paused the world, and the rest of us were losing our minds, scientists were working busily away. After all, the world was quieter than usual, and scientists like quiet. It's when they do their best thinking. And perhaps that's why 2020 marked the final push for researchers Kate Vazquez-Kuntz and Sheila-Kitchen, as they prepared to submit a landmark project for review. It was a big moment, because the brilliant duo had data to confirm that when it comes to coral, Weismann was wrong. Coral were somehow passing mutations of the body, mutations arising outside the germline, and overcoming the slow pace of natural selection. To prove it, the researchers collected eggs from a colony of Acropora palmata, which they later confirmed to be self-fertilized. Then they scanned the genome of the parent tissue, looking for novel mutations, later confirming that these mutations also existed in the eggs, meaning beneficial mutations developed in the parent's lifetime had somehow found a way into the next generation. This was a big deal. After all, it meant that an adaptive mutation occurring outside the germline could pass from one generation to the next. Okay, great. But what exactly does this mean for us again? Well, remember, coral need every tool of adaptation at their disposal if they're going to survive. And this ability to pass adaptive mutations developed over the course of their lives means each generation inherits updates, so to speak, allowing species to change faster and giving them better odds of survival amidst changing conditions. So, 2020 was shaping up to be a good year for coral. But there were still questions left unanswered. Assuming coral could break Weismann's barrier, there was still the question of how it broke it. Just how did mutations outside the germline find their way into the next generation? How were coral doing something most of the animal kingdom can't? At least, that's what evolutionary biologist Lopez-Nandam wanted to know. So to settle the debate, she and her all-star team set up their own gene flow experiment. An experiment which would unveil coral's key to longevity. Because while it did appear that mutations were moving from soma to germ, they found that it wasn't consistent. When they lined up the genomes, they only found matches 26% of the time. To Lopez-Nandam, this was a red flag. If there was a barrier-breaking mechanism, she expected it to have better success. After all, evolution would favor it. But that is when she and her team had an epiphany, because they realized that maybe they'd been looking at it the wrong way this whole time. Maybe, instead of asking whether mutations moved from soma to germ, they should ask whether that was even necessary. In other words, could the mutations have been inherited by soma and germ independently, thanks to a common ancestor? And this hypothesis would lead them to an entirely different type of cell, one that Darwin and Weismann could only imagine. One that's both common ancestor and fountain of youth, the primordial stem cell. That and more coming up next as we unveil coral's ultimate secret to adaptation and address the question of how we could make coral immortal. Stay tuned.